Well, I hope you all enjoyed that delicious Savoyard dinner. I certainly did. If I say anything particularly stupid, that's the wine talking, not me. So we're on the second of the two lectures I'm going to give about quasi-phase matching. The bibliography I promised you in the first lecture is attached to the PDF version of this file that's posted now. So in the first of these talks, I went over some background, basic theoretical considerations about quasi-phase matching, some of the basic material issues and properties, and emphasized a lot the additional degrees of freedom that are available in quasi-phase matching via longitudinal or transverse shaping of the quasi-phase matching grading, and applied some of those concepts and introduced some concepts from ultra-fast nonlinear optics. So what I hope to do today is continue in that theme of emphasizing these quasi-phase matching degrees of freedom. And in this case, one very nice example that rolls up a number of these considerations into a very apparently useful device is optical parametric chirp pulse amplification and aperiodic quasi-phase matching structures. So I will continue on that ultra-fast theme with this topic. A very different collection of things happen when you build waveguide devices. The very tight confinement and the long interaction lengths that you have available can make very efficient devices operating even with sub-milliwatt powers. And that has certainly had quite a bit of application in coherent sources. I won't really speak much about that, but we'll see how supercontinuum generation is possible through a cascaded Chi2 process in these quasi-phase matching waveguides, and how they can also be applied not as sources of radiation, but as tools for signal processing in both the classical and the quantum domains. I'm pretty sure I'm going to skip the classical part in the interest of time. I think it simply won't fit, but I put some slides in here and some review articles in case anyone was interested in this part of the story. The last topic I want to cover will be some current advances in materials beyond these simple oxide ferroelectrics we've been talking about so far, and in particular, extension of these techniques into the ultraviolet and lanthanum borogermanate, LBGO, a UV transparent ferroelectric, and extension into the mid and far infrared using orientation patterned semiconductors, gallium arsenide and gallium phosphide. The physics here of how the patterning works is very different than polling of ferroelectrics, but the optical upshot that you can make a up and down grading in the nonlinear susceptibility remains the same. So let's start in on this OPCPA story. Oh, before we do that, let me just note that there are a number of these parametric amplifier-based schemes out there with various useful applications. Optical parametric amplification I will be touching on in this next section. Also, Andrus Baltushka, I expect, will emphasize that as the main part of his talk coming later this week and early next week. Optical parametric oscillators you've heard a lot about from Majid in a couple of his lectures. I suspect Frederick Laurel and perhaps Tomas will also be speaking on that subject. And optical parametric generation is, as I understand it, a big piece of Tomas's next talk. So I will be focusing on optical parametric amplification, and in particular, how to make very intense pulses using chirp pulse versions of parametric amplification in aperiodic QPM structures. Oops, missing a picture. A parametric amplifier, as you've already heard, is a device where a pump at a short wavelength will amplify two waves, a signal and an idler wave, whose photon energy adds up to that of the pump. That's what this Chi2 box is, and that one here as well. A chirp pulse amplifier, whether it's a laser amplifier or a parametric amplifier, means that instead of seeding it with a short pulse, that seed pulse is stretched to make a longer, lower intensity seed, and hence lower the intensity that is involved in the amplification process, both typically in this preamplifier and a power amplifier, as these schemes are often implemented. And after the amplification process, the pulse is recompressed. The point of that is to avoid damage and parasitic nonlinearities that you don't want going on inside your laser or your OPA stages that would occur if you tried to amplify a compressed pulse to high energies. So this is not a new idea. The Piskarskis group proposed it back in 1992, not with QPM, of course, but with conventional materials. And some features in contrast to laser amplifiers is that you can get very high gains, parametric gains in a single pass. If you want them, it's not hard to get 80 or 90 dBs, so that's not usually the most manageable regime to operate them in. Whereas in a laser amplifier, you typically need to regenerate a low gain amplifier inside a switched cavity in order to get gains that high. So simple single pass architectures as sketched here are possible with the OPA. Some other advantages, in addition to the high single pass gain, is that unlike a laser amplifier where the gain spectrum is pretty much set by the property of the ion that's providing the amplification, the energy levels in that ion, in the case of OPAs, there is no fixed wavelength or bandwidth that they operate at. It's entirely a function of the phase matching design that you use and the choice of pump wavelengths. So you have no fixed gain bandwidth limit. And in many cases, you can get a very high contrast pulse out of an OPA more easily than you could from a laser amplifier. So in order to get a wide bandwidth in a parametric amplifier, you need wide bandwidth phase matching, just like any nonlinear process. And there are several ways that parametric amplifiers can be operated to provide wide gain bandwidths. One possibility is to pump near degeneracy, that is to have the pump frequency to be essentially twice the signal frequency. When you operate in that regime with a type 1 phase matching approach, as you detune the, say, signal frequency up a little bit, you tune the idler frequency down an equivalent amount. Their sum has to equal the pump frequency. And for a type 1 amplifier, phase matching scheme, that also implies that the K vectors are moving in opposite directions in equal amounts, so there's no first order dependence of the phase mismatch on detuning, and such a degenerate scheme can provide large angular acceptances and large spectral acceptance bandwidths, and is widely used, but is somewhat constraining because there are, as Tomas said this morning, there are a limited set of good pump lasers. And if you don't happen to have a good pump laser at exactly twice the frequency you want to amplify, you can't really operate near degeneracy. So if you're amplifying 2 micron pulses, there are many fine 1 micron pump lasers, but those same 1 micron pump lasers are not very good for amplifying a 3 or a 4 micron pulse in the mid-infrared, as is of increasing interest for high field physics these days. An alternative that allows you to escape that constraint is to go to a non-collinear operating regime where the signal and idler are counter-propagating away from the axis defined by the pump beam, and the idler angle can adjust itself to allow for phase matching over, again, a broad spectral range, and this is rather widely used, but it also has some challenges, in particular. Well, let me not get too deeply into this since we're not going to use this scheme, but one obvious disadvantage is the idler wave is of no use. It'll be spread out spatially as each frequency comes out at whatever angle is phase matched. But quasi-phase matching is often used in this non-collinear scheme, and it's a useful tool to adjust the phase matching optimally. And I suspect Andrus will be talking about these schemes quite a bit later on in the school. So an alternative way to get to these wide bandwidths we desire is to use some of our QPM engineering techniques that we've talked about. In particular, if instead of a periodic grating, we use a chirped QPM grating, then if you have a chirped structure, then different spectral components of your signal and idler can phase match at different positions in this structure, and you can maintain a collinear operation, no spatial chirp on the idler, etc. So you can also get to a nearly arbitrary gain bandwidth with such a scheme. It's simply set by how strong a chirp you apply on your grating, though we'll see there are some trade-offs there. And this is just a sketch of one theoretical design where you have basically an octave of parametric gain with a green-pumped lithium tantalate grating, a QPM amplifier with a suitably chirped grating structure. Okay, so let's look a little more deeply. This slide will get busy briefly, but I think there's some useful information buried in all this. So as we've seen in earlier talks, the parametric gain in a uniform medium goes exponentially with the nonlinear coefficient and the magnitude of the pump field in the fashion defined here. And the bandwidth of this structure is set by by the gain decreasing in this more or less parabolic fashion. As delta K increases from 0, the gain is reduced below its value at perfect phase matching, and the gain vanishes when delta K over 2 is equal to this gain coefficient gamma. So the harder you pump, the wider the bandwidth of this amplifier would be, all else being equal. Okay, so that's in an unchirped grating. In a chirped grating, you might imagine that the bandwidth is going to be set simply by what range of frequencies are phase matched, which in turn depends simply on what is the range of k vectors of the grating from the minimum to the maximum range. That will be the delta k bandwidth, as opposed to this thing related to the gain in the unchirped case. So if this grating period, spatial frequency is linearly chirped with some slope as a function of, a linear variation of the grating k vector with z, then when will there be gain? Well, there will be gain as long as gamma exceeds, delta k is less than gamma. So if a particular component of your signal and idler pair is phase matched at this position in the grating, there's a distance over which the gain is, exceeds unity, and that range depends on how fast you're changing this grating k vector. The faster you're changing the grating k vector, the steeper the slope, the narrower the range of delta k's over which you meet this gain criterion. The shorter the length over which you meet this gain criterion. And since the gain also scales with the length, as you make this slope steeper, the gain length decreases and the gain of the system decreases. So that's one of the trade-offs built into the system. But all that said, when you roll these things up, a length that goes inversely with this chirp, that came down here from the length, a length that increases with the gain coefficient gamma, together with the prefactor of gamma, you have the so-called Rosin-Bluth gain formula, which tells you that the gain of such a chirped structure is going to go inversely with the chirp rate and is proportional to the pump intensity in the amplifier. And this wobbly line here is the gain spectrum for some particular choice of parameters for such a structure, evaluated a little more carefully than what we did here. And these ripples are essentially due to the fact that any hard-edged structure like this is going to have, its Fourier transform will have ripples in it. If you apodize the structure by turning the nonlinearity on slowly at the beginning and the end, you can smooth out these ripples, and that turns out to be an essential part of making a useful amplifier of this type. We'll say a bit more about that later. Okay, so a naive picture of our chirp pulse amplifier then, if we just imagine plane waves going through it and don't worry about any of the second order effects, which turn out to be very important as we learn to our dismay. So here's a picture of such an amplifier. You launch the signal wave into it. It goes along until it hits a phase matched point. At that point, it generates an idler wave as well as amplifies the signal wave. So there's a particular point in space where that happens for one Fourier component of the input. A different Fourier component might phase match at the beginning, another Fourier component might phase match at the end. So that would give you the range of wavelengths over which you would see gain, or frequencies over which you would see gain. So another important question for such an ultrafast structure is, what is the behavior of the group delays, the group delay spectrum, or the group dispersion, group velocity dispersion behavior? And it turns out that to this level of approximation, the signal is simply amplified and doesn't see any extra phase. The phase is defined by the phase of the input seed. The idler wave, on the other hand, doesn't exist at the input of this device. So unlike the signal, where you can calculate the travel time through the structure by just the length divided by the signal's group velocity, here the idler wave is generated by something, the signal, that has moved with the signal velocity at this distance, and then the rest of the way it has gone with the idler group velocity. So you actually have a programmable delay for your idler wave by how you choose the trajectory of this chirp. So you can build in some desirable group delay spectrum for the idler, if there is one, simply by your choice of chirp function here. So you can take advantage of that concept, for example, in a tandem grading scheme like this, where you have 2 degrees of freedom, the length of these two amplifiers, and you also can choose these grading chirp functions. And it turns out you can make, if you design this device so the idler wave generated by the first stage is the input to the second stage, which then produces a signal wave. You have 2 different group delays you can adjust, and you can find there's enough degrees of freedom in here that you can design a structure whose group delay spectrum is flat, even over an octave if you want to. This, again, the same design example I gave before, and whose gain is flat over pretty much an octave in the near infrared. So there are reasons why this is a little oversimple. You couldn't actually do exactly what I describe here, but these are sort of the essential behaviors that we're going to have to understand how a more sophisticated model of this thing behaves. So another nice feature of these chirped parametric amplifiers is that they don't back convert. That is, if you take a conventional, whether it's birefringently phase matched or uniformly phase matched parametric amplifier, as you drive it harder and harder, what you'll find is you'll get back conversion. You will amplify for a while, but then various back conversion processes will turn on almost unavoidably and limit how efficiently you can operate such an amplifier. In a chirped structure like this, it turns out that you can view the amplification process as adiabatic following of a local nonlinear eigenmode. If those words don't mean anything to you, that's okay. I believe Arieh is going to give an entire lecture on that next week. So let me not belabor the meaning of that phrase, but let me show you what it looks like. This is a plot of the remaining pump power as you move through the amplifier for different amounts of input signal. So with a very weak input signal, you don't take much power out of the pump. As you turn up the input signal and hence start to deplete the pump, you find that the thing will, in a properly apodized grading, smoothly move to a certain value. If you put in more input, it again will, due to this adiabatic following process, reach a steady state and cease to evolve. And that's very powerful if you've ever tried to work with high gain, high depletion devices. This kind of smooth asymptotic behavior is really quite useful in making an engineerable system. Okay, so like I say, Adi will talk, I think, at great length about a variety of these adiabatic processes next week. Okay, so we tried this experiment, took a little low-power YAG laser, nanosecond pulse, launched into such a chirped grating. We had a tunable CW seed from a diode laser, and we just looked at what kind of gain we got. And for different chirp rates in our grating, we saw progressively wider bandwidths and the expected trade-off of the gain, and we thought that was great. But then we explored some other regions, and we saw the gain getting bigger than theory, and that usually doesn't happen. Things don't usually work better than they're supposed to, and in fact, they didn't. If you turned the chip around so that the chirp rate was in the opposite direction, you saw something even more strange, which was this thing. Gain of 40 dBs when you're supposed to get 15. It was either a patent or a disaster, and it turned out to be a disaster. This ring here is a non-collinear mode, gain-guided mode of this structure. It's not the one you want. It turns out that these non-collinear modes can see a higher gain for reasons it's probably a little too deep to get into here, but I'm happy to talk about later. Whereas in the region where it was behaving like theory said was a region where it was in fact amplifying as a collinear mode of the structure. And this obviously is a spatial mode you don't want on your output. And also, if you can amplify your signal with enormous gains in some goofy mode, imagine what the quantum noise can do. It can get amplified by that same very large gain and make noise on your output that you simply don't want. So one of the several things to keep in mind is that you need a design that suppresses this, these non-collinear modes. And it turns out that there is a bit of a trade-off. I don't want to spend the time it would take to explain this, but it turns out as you increase the beam size, you can make these gain-guided modes basically go below threshold and eliminate them as contributing to the dynamics of the system. And so it ultimately provides you with a constraint that says your mode in the device has to be at least some size to make this go away. And that in turn puts a constraint on the pump power you need, because you need a certain intensity to get the gain you want. And as you make the mode bigger, clearly you're going to have to use more pump power to reach the required intensity. So that's one trade-off in this design. Another one I already mentioned was that these ripples would be disastrous too. It turns out there's some complicated group delay stuff that goes on, as well as you'd have a very non-flat spectrum when you have this in an exponent. And so some form of apodization is necessary to smooth out those ripples and make this thing behave like a proper amplifier. And I'll talk a little bit more about that in a minute. And the last thing, last major issue that lurks in making one of these devices work in the real world is there are so-called cascade phase shifts. A sequence of two Chi2 processes can produce a nonlinear phase on the signal that depends in a complex fashion on the amplitudes of the pump and the idler wave, and we'll say a little bit more about that later. So let's take a closer look at this apodization question. What does apodization mean? Well, roughly speaking, it means you want to turn the nonlinearity on slowly and turn it off slowly as you go through this structure so that you don't have any hard edges that put high Fourier frequency components in the Fourier transform of that grading function. One obvious way to do that would be to take the duty cycle of the QPM grading and turn it on slowly up to its 50% ideal value and then turn it off slowly. While that's conceptually simplest and can work fine if you could build it, you also end up needing to make very fine features to make this thing operate properly, and those are often challenging to build. Another approach to apodization is to pseudo-randomly delete domains with a frequency that you can choose in your mask that you design to build this thing. And if you delete a lot of domains, there's not much amplification in this region. If you have every other domain present as you're supposed to, I mean flipped, you have high gain at the center, and then you can turn this thing off again by deleting more domains towards the end of the structure, which you might call a deleted domain apodization scheme. This is the easiest to fabricate. It works pretty well for low gain devices, but it turns out it's not particularly good for these high gain devices. The scheme that really works best is what's called nonlinear chirp apodization, where instead of just having this simple linear grading k-vector as you move through the device, you have a region at the beginning where it's changing rapidly and at the end where it's changing rapidly. And as we saw, the gain will drop off along with the increase in delta k. And so this effectively turns the gain on and off as you go through the structure. This one is also pretty easy to build. And it turns out it's the one that's best for this kind of adiabatic evolution. You can launch a particular one of these nonlinear eigenmodes and have it follow the structure more easily than in these schemes. And this is just a picture of what such an apodized system looks like as compared to the non-apodized one. And this deleted domain thing is a bit worse in the mid-band ripple. Okay, so we talked about the efficiency in this adiabatic following process. The cascade phase shifts are a bit of a murky thing. They depend on the sign of delta K and the phase mismatch. And as we know, the peak of the amplification is where delta K equals 0. So there is a sign flip as you go from just before the amplifying region to just after the amplifying region for a particular Fourier component. If the pump is undepleted, if you haven't seeded this very strongly, then the flip in delta K means you'll accumulate some nonlinear phase and then it will go away again because of the sign change in delta K. On the other hand, you don't want an undepleted amplifier. If you're trying to use your pump photons wisely, you want to convert as many as possible to signal and idler waves. And so if you heavily deplete the pump as you go through this gain region, then this term will also flip sign. There's almost no idler till you get to the amplification point, and then the idler number of photons will greatly exceed the pump number of photons if you've done a good depleting job here, and that will flip the sign of this term as well as the sign of delta K, which means in that regime, the nonlinear phases will continue to accumulate as you go through the structure, and you'll have something like this. And you can imagine this is a bit of a complicated thing to design around, and it turns out you have to work pretty hard at it, but Chris Phillips has written a couple of papers, which I cite here, where he shows that you can in fact manage all of these issues and end up with a well-behaved system where you get a nice spatial mode, well-controlled group delay spectra, et cetera, across the whole spectrum of the pulse. I'll talk a little bit more about how these very broadband things can be simulated, but not just yet. We'll get to that later. So an example of such a system, which is being built by, Chris was a PhD student of mine, graduated a couple of years ago. He joined Ursi Keller's group and is now working at ETH on building some of these kind of parametric amplifiers for some high field physics experiments that she wants to do in the mid-infrared. So the goal is to get a few cycle pulse in the 3 to 4 micron part of the spectrum, and rather than have a low, like kilohertz rep rate, very energetic pulse system, she's interested for the class of experiments she wants to do in a very high rate system, 50 or 100 kilohertz with lower pulse energies. So you don't need to see this whole thing, but the nut of it is there is a picosecond pulsed, 2.6 picosecond, 50 kilohertz neodymium vanadate 1 micron pump laser, which is used to pump 2 different preamplifier stages as well as 1 power amplifier stage. So it's a 3-stage optical parametric amplifier designed so that when you're all done with this thing, the chirp on this pulse can be compressed simply by passing it through a bulk block of sapphire. So it's the world's simplest pulse compressor. No need for low throughput gratings and the like, which is useful. One useful feature being able to design the group delay behavior of the system. So 40 femtosecond pulse was retrieved here at the end of this structure. Previously it was about 12 microjoules at 50 kilohertz, but more recently it's, the spatial mode is beautiful. And more recently, the thing has been improved a bit to 17 microjoules, more than half a watt of average power in these femtosecond mid-infrared, few cycle mid-infrared pulses. This is a graph of various of the OPCPA functions in the mid-infrared various people have been building. These are the ones that we've just been talking about. So the pulse energies are not the highest, but the rep rates are in the 100 kilohertz range. So these deliver a lot of average power. And Ursi being Ursi and has a lot of money and ambition, she's hoping to scale up the pump laser to make it possible to produce half a millijoule at 100 kilohertz, so that's a frightening 50-watt few cycle mid-infrared system. Okay, so that was a number of these QPM concepts rolled up into the Chirp pulse parametric amplifier. Now let's take a look at something kind of at the opposite end of the world. We're not making hundreds of megawatts of peak power. We are making milliwatt power devices using waveguides. So there are a couple of reasons why these things are of interest for our purposes. The more obvious one has to do with the fact that, as Benoit discussed in his introductory talks, there are trade-offs when you focus a free space nonlinear interaction through a crystal of a certain length. Because the efficiency increases with the square of the length, but also with the intensity, there's a trade-off between a tight focus for high intensities and a short interaction length versus loose focus for a long interaction length. And when you're all done, the efficiency of this kind of device will scale only with the length, not with the length squared. In a waveguide, of course, once you focus the light into the waveguide, it's in the waveguide, and you maintain the same size spot for however long the device is. Oh, look, I didn't get all the I assured everybody that I had all the font errors out. But it turns out that who L squared was not the intended phrase right there. But the efficiency, which should have been eta, does scale with the square of the length as opposed to linearly in the length. And also the tight confinement that you can have on the order of a wavelength in size means that you can have high intensities for relatively low powers. And it's, in fact, the spatial overlap of the modes of this structure that define what the effective area of a particular interaction would be. So if we compare a typical bulk quasi-phase matched medium in the visible for SHG, say, you might have a few percent per watt per centimeter efficiency in a bulk device, and a typical number in a well-designed waveguide, it's 1,500% per watt centimeter squared, so enormously higher efficiencies, several orders of magnitude higher efficiencies, as well as more advantageous length scaling in a waveguide. A less obvious, but in many cases, for example, for quantum signal processing, you really want a high quantum efficiency device. You want to drive the system very close to 100% conversion. In a bulk medium, that's a bit tricky because you have, in your Gaussian beam, non-uniform conversion. When you're, say, in a low conversion regime, the shape of your generated wave will look more or less like the shape of what's doing what your input was. But in a high conversion regime, you can start to get non-uniform conversion across the aperture of a Gaussian or other non-flat beam. In a waveguide, the interactions between discrete spatial eigenmodes of the structure, and you can't deplete the middle of an eigenmode and not the wings. That's not how waveguide modes behave. So you will uniformly deplete this mode's amplitude, and it will remain the same mode shape. So these things are much easier to drive into the high conversion regime, and we'll see some examples of some 99.9% efficient nonlinear devices that we can build taking advantage of the high gain and uniform conversion available in a waveguide. Let's not bother with that. So a lot of people call me up and say, I tried to do this or that waveguide experiment and it didn't work anything like theory said it would work. And there are a number of additional considerations, even if you're fairly familiar with bulk nonlinear optics, that make waveguide nonlinear optics a little bit different. One difference that's often quite important is while most bulk media have very low losses, if they're of any high quality nonlinear crystal, in waveguides it's rare to see losses much, unless you've got a glass fiber or something, much below 0.01 inverse centimeters. 0.1 inverse centimeters isn't rare, and waveguides in development or in complicated material systems can easily have in excess of an inverse centimeter of loss. So you need to be aware of this stuff as you're thinking about could you do your desired experiment in a waveguide. These excess losses come from usually some form of roughness on the edges of the waveguide, possibly surface imperfections as well. Typically, the losses increase with the index contrast. The larger the core to cladding index difference of the waveguide, in most cases, again, all else being equal, the losses will get worse. But we also saw that the confinement gets better. The larger the delta n of your waveguide, the smaller the modes are going to be. And so there's a bit of a trade-off again. You might want a large index contrast in order to get to high gains per unit length, but you often buy that at the price of higher losses. So again, that's another thing you need to think about as you try to design an experiment with one of these things. You're probably not going to put 100 watts through a typical waveguide. The small mode area leads to very high intensities. That's the point of the waveguide, high efficiencies at low powers, but it also means you can have rather unmanageable average power loading, average intensities if you try to push too much power through these structures. And usually 100 milliwatt to watt kind of powers are quite plausible, but 10 or 100 watts, you're going to get in trouble. A little more subtle issue is that, again, most modern, I'm old enough to remember when this wasn't true, but most modern nonlinear crystals are reasonably homogeneous. You don't have to worry too much about the refractive index varying along the length of the crystal due to people like Benoit doing a bad job of growing that crystal. But most of the technologically important nonlinear materials are now at a stage where that's not a major concern. But in a waveguide, there's another way for the phase behavior to be inhomogeneous, and that is if the waveguide fabrication isn't perfectly straight, if there are some variations in the width of the waveguide, those will translate into phase velocity variations, and they will act on your interaction the same way that a compositional inhomogeneity would have acted in the old days on a bulk crystal. So that may limit the useful length of your device. But well-developed waveguide designs, you can come up with so-called non-critical designs without first-order sensitivity to these minor geometrical variations. And well, yeah, I'll show you in a minute. Well, let me show you. This is a 5 centimeter long reverse proton exchange waveguide in lithium niobate, harmonic generation of a 1.5 micron laser. You can see you get very high efficiencies, 3% per milliwatt. That's 3 or 4 orders of magnitude higher than in a bulk crystal, and you can also see a very clean sync curve indicative that it's a very homogeneous structure. So it is possible to build waveguides that behave decently. Oops. The exact details of how you build these waveguides are not terrifically relevant to anything we're talking about, but just to give you an idea of the kind of processes that will often take place. Some photolithography will be done to open up a channel in a mask. And this is for reverse proton exchange, lithium niobate. There's an ion exchange process. Protons are put in. Lithium comes out. You make a doped region in the surface of the waveguide. A thermal annealing step at a few hundred degrees will drive those protons in more deeply. And then a second ion exchange will pull some of those protons out, so you end up with a buried waveguide. It turns out that a symmetrical waveguide structure is quite important for nonlinear optics because with an asymmetric waveguide, the different frequency the pump signal and idler, for example, will have their peaks at different distances below the surface. So the overlap of these modes will be very bad. In a symmetrical waveguide, while the size of the modes will depend on what frequency, what wavelength the mode is, the center of the mode will always be at the center of that symmetrical profile, so you get a much better modal overlap. So just some of the considerations if you ever do start to think about developing a waveguide process. Okay, so once you're talking about having a waveguide process available, you can think about integrating many more pieces into your nonlinear device than you could easily do in a bulk interaction. You can have adiabatic tapers to launch the light efficiently into your waveguides, power splitters, wavelength multiplexing couplers, tight radius bends. You can build spatially placed waveguides to interact with different QPM gratings to interact with different portions of the waveguide. You have quite a few degrees of freedom in this kind of structure on top of the additional degrees of freedom that you just got from choosing to do a quasi-phase matched interaction. And we'll see how some of those can be taken advantage of. That proton exchange process I talked about is not the only kind of quasi-phase matched waveguide out there. The Paderborn group, Wolfgang Zoller, though he's now retired, but his group did some very nice work with titanium waveguides and lithium niobate together with quasi-phase matching. There's another interesting family of techniques which we might call machined techniques, where a lithium niobate wafer is bonded to some low index layer, silica, maybe some epoxy, to make a slab waveguide, mechanically polished down to a few microns thick, and then a ridge is defined mechanically either with a diamond saw blade, believe it or not. This edge here came from a diamond saw blade. That's a 10 micron bar you're looking at there. So some amazingly smooth surfaces can be generated by these means. Or with more difficulty, you can do some kind of reactive ion etch to define these channels. The nice feature of these waveguides is they're just virgin lithium niobate in here, no dopants, and that can have some technological advantages, which we probably don't have time to touch on. If you actually want to use one of these devices, it's again a little different than a bulk device because you have to get the light in and out of your structure, which is not always easy. But just to show you the amazing packaging technology that can be done if it matters, this is one of the original driving forces for working on lithium niobate quasi-phase matched waveguides was to make a 400 nanometer source by doubling an 800 nanometer diode laser in the era before gallium nitride semiconductor lasers. For optical data storage, a little compact source of UV light was of interest. And NGK and Matsushita worked together on this little thing. This guy here, this little package on the person's finger, contains a silicon submount, a QPM chip, and a 820 nanometer diode laser butt coupled to this thing. So this whole little guy, I won't talk about all of the clever engineering that went into it, but they could get 100 milliwatts out of that little box into UV. So had the gallium nitride technology not come along, probably we would be seeing these things in Blu-ray players instead of gallium nitride diodes. Let's not talk about that. Okay, so I said I was going to talk about continuum generation. I wasn't going to talk about the various kinds of simple coherent sources that can be built in these waveguides. So let's take a look at that point. So we've said that less than 100 milliwatts, in fact, in many cases, just a handful of milliwatts of CW pump light in the infrared are enough to do a very efficient frequency doubling process. So you might ask what would happen if you launched that same 100 milliwatts not as CW radiation, but maybe as a few hundred femtosecond pulse train from a mode-locked source. And what happens is you get a supercontinuum that comes out of the waveguide. This rainbow here is a supercontinuum, probably reminds you of the ones based on Chi-3 phenomena that you've seen in photonic crystal fibers or other techniques that have been used to build supercontinua based on Chi-3 processes. It was not at all obvious what the mechanism in this Chi-2 medium was for generating a continuum. It turns out the explanation is that it's rather similar to the Chi-3 phenomenology, but instead of the nonlinear phase shift, the nonlinear refractive index coming from a true Chi-3, they come from a cascade of two Chi-2 processes, so-called Cascade Nonlinearities. So we need to understand a little bit about those to understand how these things work. So One way to visualize, I mean, you can just solve Maxwell's equations and you can see that you get a cascade, you get a nonlinear phase shift in a phase mismatched high efficiency SHG process. A bit of a physical insight maybe could be gotten from a picture like this. Let's say you launch a beam at frequency omega, a pump, into a nonlinear crystal, and the phase mismatch is pretty large, so you never make much second harmonic. You stay most of the power stays in the pump, but a little of it converts to the second harmonic and then converts back to the pump. Well, the phase velocity of that harmonic was different in the pump. That's why it's phase mismatched. And so after this converts here and moves a little distance at the phase velocity of the second harmonic, when it converts back to the pump, it will convert back with a somewhat different phase. And so it will lead to a phase shift on the remaining fundamental beam. If I pump it harder, turn up the intensity of that fundamental beam, a larger fraction of it will convert and then convert back to the fundamental. And so if there's a larger fraction moving with this different phase velocity and then converting back, you might imagine you would get a larger phase shift. In fact, in some limits, it is proportional to the intensity, this extra phase shift, so it mimics a chi3. If you reduce the phase mismatch so that there is a larger fraction of the radiation converted to the harmonic and then back to the fundamental, unsurprisingly, as you increase this fraction, again, you get a bigger phase shift. So if you do this a little more carefully, do a proper multiple scale analysis of the coupled wave equations for the harmonic generation process, which you can find in that reference if you want, what you find is that the evolution equation for the electric field at the fundamental contains the usual dispersion term, and then it contains this piece, which goes like chi squared over delta k. So the more nonlinear conversion you get, and the smaller delta k, the same argument we had here, oops, you will have an effective chi3, which scales like the square of a chi2 and 1 over the phase mismatch delta k. If you take the next order of this multiple scale analysis, you get a term that is reminiscent of a Raman-like term, except it's now going like chi2 squared over delta k squared with a group velocity mismatch thrown in. So the upshot being that at least semi-quantitatively, if delta k is not too small, obviously as delta k goes to 0, this analysis fails, but you can see how you get a cascade phase shift in effective chi3 based purely on chi2, and that you can control the size of that effective chi3 through the size of delta k. And we'll even say a little bit about these Raman-like behaviors later on as well. But intuitively, this can help explain the kind of phenomena you see in these phase mismatched processes. You can visualize them as an artificial chi3 and one whose trajectory you can program through your choice of delta k versus z. In a conventional medium, of course, delta k is what it is, but in a quasi-phase match structure, you can change the gradient k vector and hence change delta k. So given all that, why would we want to do supercontinuum generation in a chi2 medium when there's already a number of chi3 based schemes out there that you can use? Well, one thing is in a chi2 medium, you get self-second harmonic generation going on, and so you can, without further ado, just look at the output of one of these continua and often see the carrier envelope offset beats between one end of the spectrum self-harmonic generating and interfering with the other end of its spectrum without going through a separate frequency conversion stage. As I said, you can control the sign and magnitude of this artificial chi3 via your choice of delta K, which means, for example, you could have a soliton in either a positive or a negative dispersion regime just by choosing the right sign of the chi3 effective by choosing the right sign of delta K, or equivalently, the right grading K vector. And finally, as I said, you can engineer trajectories of this nonlinear behavior, the chi3 through the medium, or perhaps generate a supercontinuum and then amplify a section of it in OPA, et cetera, through the use of the various grading engineering techniques we've already spoken of. So how would you model such a process? Well, this cascaded chi2 is nice for heuristic explanations, but it's really insufficient to do a quantitative model. It's obviously going to fail as delta K approaches 0, and it's useful for guiding your design thinking, but it's not useful for quantitative calculations. You might try the usual coupled mode equations for the fundamental and the harmonic that we've seen many times, and that will work for a while, but once you get to the regime where the spectra overlap, the fundamental and the harmonic, it's entirely unclear in this kind of system how to describe that overlap region. As has been done in the chi3 world, you can write a single envelope model based on some concepts of general unidirectional propagators, and that does work to simulate these gratings. There was some work by Conforting and colleagues who first added the chi2 terms to these single envelope equations. Such models, if they want to actually properly capture the behavior of our continuum, need to include chi2 and chi3 effects, arbitrary quasi-phase matching profiles. Typically, multiple waveguide modes are involved and multiple orders of your quasi-phase match structure. And the basic assumption buried in this is that you are neglecting the backwards going wave, which is almost always okay. So these things work. Oops. Chris Phillips, the same fellow I was mentioning, has a couple of papers showing the application of this kind of technique to analyzing supercontinua. More cleverly, Chris came up with a multi-envelope model, so something that looks more like this, but properly accounts for all of the processes, including those occurring in this overlap region, and can assign to the right envelope the right mixing terms. I won't even pretend to go into the details of that. It looks something like, oops, that was probably not the button I wanted to hit. It looks something like this, but it turns out, that's what I said too when he showed it to me. Chris is, I don't know if any of you have worked with Chris at ETH, but he's just a brilliant fellow. In any case, by defining separate envelopes for the pump, signal, and idler, and whatever sum frequency or harmonic terms you want to address, it can properly account for the interaction of these various envelopes, and by having the problem broken up in this fashion, it allows you to model and isolate the various key processes in ways that are just not doable with a single envelope process. And it turns out the computational efficiency can be substantially higher for this multi-envelope model. It's not really that well known, but here are two references, and if you are going to do any of these kind of computations, I would encourage you to take a look at Chris's papers. They're actually very good. Okay, but the upshot is not how cool the paper is, but how well does it work. Here's an experimental picture of a continuum generated with 150 femtosecond, 1043 nanometer pulses in QPM gratings that were chirped with two different rates, 7 to 11 microns or 7 to 9. No, this one's unchirped. And comparing the chirp case here, the experiment and the theory look remarkably similar. Again, getting into the details of explaining this trajectory of the intensities as you move through the crystal is a long story and probably not too interesting for us. But if you're familiar with the chi3 continua, it's a very similar sequence of steps involved, though with different importance. The pulse will self-compress, rapidly increase in its intensity. A number of simultaneous nonlinear processes will occur, and then a supercontinuum will form. But let's not belabor the depths of how that happens. Another important point is that when you have this chi3, a true chi3, and this cascade chi2, you can be quite sensitive to various competitions between the processes involved. And this is a graph of the output of Chris's model for 3% change from the top to the bottom here of the electronic chi3. And nobody knows the electronic chi3 of lithium niobate to 3%. Who are we kidding? That's just not just how the world works. In fact, Chris did quite a bit of work teasing out the proper electronic chi3, Raman chi3, chi2 numbers for lithium niobate. And one point you might want to be aware of is there's a widely published number for the chi3 of lithium niobate. It turns out that that was done by the Z-scan technique that you've heard about. And the authors did not separate out the cascade chi2 from the true electronic chi3. So what their paper actually gives you is the sum of those two numbers. And that's very different than what the electronic chi3 is. And when Chris first ran this model, it had no resemblance to the outcome of the experiments because he was using this wildly wrong chi3. But when he subtracted out the cascade contribution and properly determined what was the electronic chi3 and what was the cascade chi2 piece, then you got these beautiful agreements between this very complicated theory and these experiments. So one last quick look. Chris tried a 2-micron pumped supercontinuum generation with 100 femtosecond pulses from a thulium fiber laser in the vicinity of 1.9 microns. And this is really remarkable. This continuum extends from 500 nanometers to 3 microns. And the blue line is the simulation with no free parameters in it. And this black line is the, sorry, I said that backwards. Black line is the simulation with no free parameters. The blue line is the experiment. So I think we can say we understand these things. And one interesting feature, like I mentioned, is just looking at the output of this, you could see F2F beats. If you looked in the vicinity of 1200 nanometers, you could see 2F3F beats if you looked around 750 nanometers. And you could see 3F4F beats if you looked in the vicinity of 500 nanometers. So all of these were present, and this one here was present with 30 or 40 dBs of signal to noise and 100 kilohertz bandwidth. So this was more than adequate for doing CEP stabilization of a laser system like that thulium fiber. Just a couple of other examples of this kind of thinking. I said there is a cascade Raman-like behavior that emerges from this multiple scale analysis. This is an experiment where 2-micron radiation of, I think, about 150 femtoseconds was launched into such a waveguide. And as you turned up the energy in the pulse, you see something that looks just like a Raman self-frequency shift. But with the real Raman coefficient of lithium niobate, you'd see nothing like this. It's not nearly big enough. And if you compare it to the experiment based on this cascading, you see that this Raman self-frequency shift term very closely predicts what you see in the real system. Those aren't too bad agreement. Another class of devices you can imagine building is the one I mentioned where you can engineer a trajectory of this effective chi3 by engineering the trajectory of your grading k-vector because of this dependence on 1 over delta k of this cascaded chi3. And so here's a calculation Chris did where he took a QPM period, kept it constant for a while, ran it through some trajectory like this. The point being to do something akin to dispersion decreasing soliton compression, except here the dispersion is constant, but the chi3 is increasing because of the approach to phase matching. So here you're accumulating some self-phase modulation, you're turning this thing up and compressing the pulse, and then you see the corresponding pulse duration going from a few hundred picoseconds and compressing down to 15 femtoseconds through this trajectory of Chi3 effective. And in principle, this thing should be an 80 or 90% efficient soliton compressor and would be a nice component of such a continuum generation system. Okay, let's not belabor that. I think I've said most of these things throughout the talk. With the orientation pattern gallium arsenide that we will talk about shortly, it will be possible to extend this kind of thinking not just out to 4 or 5 microns, but all the way across the mid-infrared to 12 microns or farther. And much as group velocity engineering is essential for Chi3 devices, it's not essential for these devices because of the other degrees of freedom we have, but it can be quite helpful. And this is, again, a simulation of what one could do with a little bit of dispersion engineering by making one of those tightly confining waveguides I showed previously. And you could get supercontinua with high efficiency at just 60 picojoule pulse energies. So it could be, again, quite a technologically valuable system. Okay, so up to now, I've been talking about various flavors of coherent sources, primarily ultra-fast coherent sources. But if you have devices that have efficiencies measured in percents per milliwatts and can be phase matched flexibly and have very broad bandwidths and fit into centimeter cube volumes and operate with milliwatt pump levels, you might ask, can we do something that goes beyond simple coherent sources? Can we do some kind of interesting signal processing? And the answer, it turns out, is yes, both in the classical communication world and in the quantum optics world. There are a number of quite interesting things that have been done over the last 10 years using these kind of tools. Let me only briefly talk about this classical scheme, the kind of things one can do. Like I said, given our time, I don't think we should try to get too deeply into any of the real devices. But let's take a look at the difference between the RF signal processing world and the optical signal processing world. In the RF world, mixers are used omnipresently. It's hard to picture any RF signal processing scheme that doesn't have a mixer in it somewhere. And it's very easy to make an efficient mixer in the RF because we have extremely nonlinear elements. Diodes will transmit current in one direction and not in the other. So you can take a sine wave and make this out of it. And that means that little circle with a cross in it that appears on your circuit diagrams can be a lumped element much smaller than the microwave wavelengths that it's manipulating. The local oscillator that you mix with your signal, typically you want to know how many dBm of local oscillator, how many milliwatts of RF power does it take to make this mixer operate efficiently. And when you put in 2 quasi-sinusoidal inputs, you get local oscillator plus or minus the signal. So these are cheap and easy. In the optics world, you could imagine a similar functionality. You put in some pump and you put in a signal and you get out a mixed product, the idler wave. And why wouldn't one want to use this to do signal processing in the optics world? Well, the basic reason is we don't have nonlinearities like this. We have very weak nonlinearities. You end up having to build a distributed mixer of, we talked at length now about how one does that. And at least in the bulk world, you needed 100 watts or a kilowatt or something to make an efficient nonlinear mixer, and they had narrow bandwidths. So who the heck would use such a thing? Well, nobody. So this kind of signal processing didn't really happen in the optics world, but now that we have devices with those kind of properties, it becomes possible to think about doing exactly the same kind of, well, very similar kind of processing to what is common in the electronics world. For example, if you have a signal and one of these optical frequency mixers, you can put in a CW local oscillator and shift the carrier frequency of that input without changing the amplitude or phase structure of the information that's imposed on your carrier. If you clock your local oscillator, you now have a sampler or a demultiplexer or a multiplexer. You only get an output when you've got something at the input and something, a pulse from your clock. And because of the phase conjugating nature of these kind of difference frequency mixers, you can also build spectral inverters, phase conjugators, mid-span spectral inverters being interesting for dispersion management and in communication systems. So, like I said, there's some very interesting performance numbers you can get out of these waveguide devices. We've said a few thousand% per watt. You can get 70 nanometers of mixing bandwidth, terahertz switching rates, 50 dBs or more dynamic range, and you only need 10 dBm of pump power. So these are neat, and there's a lot of examples in the slides. I won't talk about them. I'll note that I've given you some review articles. They're in the bibliography. If you want to read about this kind of classical signal processing, there are a lot of places to do it. But what I think I should talk about instead are quantum frequency conversion devices. We had a vote last lecture, and I think the thing that had the lowest number of votes was the classical signal processing. So let's skip that one. It's a democracy here. And let's talk about these quantum frequency conversion devices and see what we can do in that part of the world. So why would we want a quantum frequency converter? Why would we want to be able to take a single photon from the red and move it to 1.5 microns or something? Well, basically the issue here is in some kind of quantum network, you typically need single photon sources, perhaps nitrogen vacancy centers at 630 nanometers, maybe quantum dots at 910 nanometers. You need some kind of quantum memory, maybe a rare earth ion in a suitable host crystal that has a set of discrete lines, none of them being these. And then, of course, you want to interconnect these things with optical fiber at 1.5 microns. And so how are you going to take this heterogeneous collection of devices and make them in some fashion interoperable? Well, if you had a way to efficiently, with high quantum efficiency, convert, say, 637 nanometers to 1550 nanometers, send it down a fiber, and then send it to your memory operating at 1.1 microns, or whatever it is, you would have a way to choose the best device for each of the functions that your network requires, and then use these guys as simple interfaces so that you can have one talk to another. This is not a new idea. Prem Kumar first discussed quantum frequency conversion back in 1990. The basic concept being if you put in a classical pump and a weak or single photon signal, you can sum that guy with the single photon and produce a single photon at the sum frequency. You could equally well, hang on a second, and you simply, when you drive this thing, the mixing efficiency here goes like the pump power and the parameter of the waveguide. And when this guy equals pi over 2, you have simply transformed the operator representing frequency 1 here to frequency 2 and vice versa with, in principle, perfect fidelity, a conversion ratio that goes like sine squared of the square root of the power here. Okay, so that's what you think should happen theoretically. And if you can build such an efficient upconverter, an obvious example of something you might do is convert single photons at 1.5 microns to 700 nanometers. That would let you count them with silicon avalanche photodiodes, which are much more attractive than InGaAs or 3.5 APDs. Perhaps not as good as the best superconducting detectors, but on the other hand, that's a room temperature system. If you did a down conversion device where you put in, say, a red photon and mixed it with your classical pump, you could produce a longer wave output. So conceivably, you have a barium ion source of single photons in the red. You mix it with a 1 micron pump. You can convert those photons to the 1.5 low loss region of silica fibers. So flexible interoperability if you can do this efficiently and you can do it with low noise. So this was first tried seriously by, in a CW converter by Franco Wong's group back in 2004. He made a little ring cavity around a bulk Piplin crystal and pumped it with 1064 nanometers. That resonated up the intracavity power to about 20 watts, which was what was necessary to do decently efficient mixing of a 1.55 photon and converting it up into the into the visible for detection with a silicon APD. So he got to 85 or so % quantum efficiency, which ain't bad. But if you look at this other line here, he also got to a few 100,000 dark counts a second, which kind of obviates the utility of having a good photon counter if all the photons it's counting are noise photons generated by your up converter. And it wasn't clear what the origin of those dark counts was. At roughly the same time, we built a traveling wave waveguide device with a similar concept, classical pump, weak signal source at 1.5, up converted into the near infrared. As I said, it's not hard to make these guys work efficiently. At this point, 99.9% of the input photons were being converted to the sum frequency. So that's fine. But we also had 10 to the 5-ish dark counts per second coming out of this device, just like Franco did. And we didn't understand why we were getting, oh yeah, and the power required was about 100 milliwatts, and this is that sine squared of square root of power story that exactly fits what you'd expect from the calculation. So we didn't know what that dark count stuff was about. The structure of this device was pretty simple. There was a mixing waveguide. To do any interesting quantum optics, you typically want low losses. That means you have to efficiently couple from your inputs to your device and out again. With suitable adiabatic tapers, you can get nice round input modes, couple them to fibers. Like I say, the quantum efficiency of this thing was fine. The problem was these dark count. Yep, there was my message. Efficiency is easy. Low noise is hard. And that's the battle we had to face. So you may remember in my first lecture, I talked a bit about what happens when you have random duty cycle errors in one of these quasi-phase match structures, that you could picture this thing as the sum of a perfect pattern plus a bunch of little up and down errors. And the Fourier transform of that was the Fourier transform of your perfect pattern and the white noise that comes from Fourier transforming those little up and down errors. And so there is a pedestal on the spatial frequency spectrum of such a perturbed structure. And this turns out to have been the key to understanding where the extra noise came from in this set of experiments. What happens is something like this. The process you want is that this pump mixes with your single photons here, converts them up to the output at omega 2. The noise comes from spontaneous inelastic scattering. And you might imagine Raman-Stokes photons could overlap with your signal wave frequency and make some noise. If you work it out, it won't. For the combination of wavelengths, it's too far away. But there's this spontaneous parametric fluorescence, a process that's not supposed to be phase matched. If the process you phase match is this plus this equals that, this minus this, making something off in the mid-infrared, should be badly phase mismatched. And it is. But if you've got this white pedestal here, it says that, okay, you've made your process for the designed interaction 100% efficient. Okay, your undesired parametric fluorescence is maybe 3 or 4 or 5 orders of magnitude down. But if you're sending 10 to the 18 pump photons per second through this thing, if you have 10 to the minus 5 efficiency, you can still get a lot of this nominally non-phase matched process, nominally phase mismatched process to occur, and it's these spontaneous parametric fluorescence photons from this disorder phase matching that creates the noise in these things. If you calculate the tolerance that would be required on the perfectness of your domain pattern, you can tolerate nanometer-ish errors if you want to get down into the tens or hundreds of dark counts per second. That's not going to happen. So your only real option is to use a pump wavelength, a frequency that is lower than any frequency of interest for your system. Then all of these spontaneous photons will be at longer wavelengths, at lower frequencies. The Stokes-Raman, your spontaneous disorder phase matched parametric fluorescence, and the only thing left to bother your single photons is the anti-Stokes-Raman. So going to a long wave pump turned out to be the key to making these guys low noise. One issue, of course, is if this pump frequency is less than omega 1, say less than 1.5 microns, then even if you tune to just below the pump to just below 1.5 microns, the best you can do is get to a frequency that is twice this. And so if you want to work in the visible, where your output is more than twice your input, you can't keep the pump at a frequency lower than your input. So the solution to that problem is to use a so-called two-step mixer. So if you take a long wave pump and you sum it with your 1.5 microns, you get to some intermediate wavelength, say 830 nanometers in this example. If that same pump then mixes with this 830 nanometer photon, it can produce a visible photon because you've now used two pump photons to shift up. And so that gives you much greater freedom in operating with long wave pumps and evading this noise problem. And of course, it's easy to do two sequential mixing processes. You just put two different QPM gratings in your waveguide, and you have two different mixing processes. And so you can integrate this structure quite easily. And when you do that, you end up with a quantum efficiency of about 90%. And the dark counts were a few hundred. And it turns out they are dominated by this goofy shoulder on the Raman cross-section, making the anti-Stokes a bit worse than you would expect it to be. But still, if you're at a few hundred dark counts a second instead of a few 100,000, you've now put this thing in a regime where it's actually useful for doing quantum optics. And you could exactly explain the excess noise now by the spontaneous Raman scattering rather than by this disorder phase matching. All right, let's not belabor that. One last family of thoughts before I leave this quantum frequency conversion and move on to these new materials, the UV ferroelectrics and the semiconductors. While I've been talking about CW pumping of these devices, being able to manipulate the temporal or spectral structure of your single photons could be a very valuable tool. The simplest such concept might be to time gate the conversion of a single photon at a speed faster than you can conveniently resolve with any single photon detector. The speed with which you can do the gating is set only by the pulse of your classical pump laser, and so you can time resolve structure in at speeds that are just not accessible to single photon detectors. So in the interest of time, I won't talk too much about this experiment other than to note that it was interesting to analyze a quantum dot that had sort of a 600 picosecond spontaneous lifetime. Look at upconverting single photons with a 10 picosecond gating pulse. This was a long story as to why this was a valuable experiment for understanding the dynamics of the spin behavior in that quantum dot. But the upshot is you could trace out this behavior with roughly 10 picosecond resolution using this kind of gated up conversion process, down conversion process rather. So where might this kind of process go? Well, I think while I talked about simple gated conversion, you could do much more sophisticated manipulation of these single photons. For example, if you had a chirped classical pump converting your single photon, you would impose all the phase structure of this pump onto your single photon, and then you could put it through a conventional pulse compressor and have, for example, a much shorter single photon than you started with. And this kind of spatiotemporal shaping, or time to wavelength conversion, spectral correlators, there's a whole family of single photon manipulations with classical pump beams that are possible using the high efficiency of these structures. Let me not beat that to death either. Well, we don't have time to do this, but this one is kind of fun. So let me just take a second to talk about this. If you make a mixer, whether it's a classical one or a quantum one, and this is probably more interesting in the classical regime, this is an example of a case where you have taken a bunch of inputs at 4 wavelengths in the vicinity of 1.5 microns, mixed them with a pump, and converted them to mirror image around that pump wavelength through a difference frequency mixing process, a useful function, say, in wavelength division multiplexed communication systems. It's easy to see how you could spectrally filter the input and the output of this thing with a simple beam splitter. You could tell this guy from this guy if it was a suitable dichroic coating. What would happen if I tried to tune this thing into degeneracy? Well, then how would I tell the inputs from the outputs if they are at the same wavelength and the same polarization? Well, spatial modes are a knob you can use to do that. Imagine that you have your input in an odd mode, and you mix it with an odd mode of the pump, and you generate an even mode as your output. Well, if you have a suitable structure for separating even and odd modes in your waveguide, you could easily then, even at degeneracy, distinguish your input from the output. It turns out that an adiabatic Y-junction is just the kind of device that will do that job for you. If you launch in the skinny arm, it will evolve adiabatically into the first higher order mode. If you launch into the fat arm, it will evolve into the fundamental mode. And equivalently on the output, you can separate those things with a similar asymmetric adiabatic Y-junction. So you can use this kind of structure to create distinguishability at degeneracy, not using polarization, which is inconvenient because you want to use the large nonlinear coefficients of this material, but through the spatial mode combinations you choose to operate with. And so this is an example of such an asymmetric Y-junction for doing this, either preserving the 0-0 mode or launching the odd mode, and you can get about 30 dB selectivity between these two arms using this kind of technique. And we built, and one other issue that arises is the modal overlap of an odd mode with 2 even modes vanishes just by symmetry. But you can break the symmetry by skewing the QPM grading 180 degrees on either side of the waveguide or putting a tilt in it. And in that case, you can even interact even and odd modes with nearly the same efficiency that you could mix even modes in a symmetrical structure. So you have all the building blocks for making this kind of efficient, distinguishable, even at degeneracy kind of wave mixer. And again, the details are probably not terrifically relevant here, but the fact that we have this degree of freedom is in fact quite valuable and useful. Last thing I want to say about waveguides before we go on to the new materials in a bit of a rush is historically most all the waveguides used in these quasi-phase matching media were built by diffusion, which means they are weak waveguides, they have a low index contrast, you can't do much group velocity dispersion engineering, you can't do all the neat things that the silicon photonics and silicon nitride photonics world have been doing with nanophotonic waveguides. And it turns out that it's very difficult to chemically etch lithium niobate, so it's very difficult to form the kind of nanostructures that you would like to use to move these Chi2 effects into the world of this nanophotonic stuff. But there are now a couple of groups doing a very clever thing where you may be familiar with the ion slicing approach to cutting wafers. You do an ion implantation and make subsurface damage in a wafer of lithium niobate. You can bond that to another substrate, perhaps a silica substrate. Thermally shocking it, you will crack that damaged layer, and you can put a micron of lithium niobate single crystal on a silica substrate, chemomechanically polish that, you have a planar waveguide, and then you can pattern tantalum oxide, you can pattern silicon nitride, you can pattern silicon, and make a composite waveguide with very high delta N and tight confinement, and move towards combining nano waveguide effects with Chi2 effects. And I think this is very exciting work. This group here is at Creole in Florida. There's a couple of others doing the same thing, and you could really make a whole new spectrum of devices if you really could combine Chi2 effects with systematic group velocity engineering. But those aren't quite at the stage we need them to make serious devices yet. Last family of topics, I'm sure you're sorry to hear in our last 3 minutes, maybe 4, are some new directions in quasi-phase matched materials. And so you could ask, well, why do we need new materials? And these oxide ferroelectrics, they're easy to pattern, they're readily available, they have nice performance, but they have some fundamental limits. One of them is that almost all of these oxides have multiphonon absorption that turns on in the vicinity of 4 microns. So if you want to do any work in the mid-infrared, these guys just aren't going to transmit the light. And similarly, in the ultraviolet, most all of these oxide ferroelectrics die somewhere in the vicinity of 350 or so nanometers. They start to have strong electronic absorption. A second class of issues is that you can get big bulk crystals, multi-centimeter apertures, but it's hard to make these periodically poled materials much thicker than a few millimeters, and that puts limits on the size of the beam you can put through them, and that puts limits on the peak powers you can transmit without damaging the surface of the crystal. So they are a bit limited for high peak powers. And then there's some extrinsic problems, residual absorption, aging phenomena. These turn out to be the last talk I'm going to give tomorrow about parasitic effects in nonlinear frequency conversion. Don't blame me. Benoit asked me to give that talk. But let's not look at these. This mostly involves improving the properties of our existing materials, but these are intrinsic, at least this is an intrinsic limit, and we have to go to some other material to fix it. This we might be clever about our geometries and fix. So let's take a quick look at how we can deal with this small aperture problem. To deal with that problem, you might say, well, why don't we come in on the surface of this lithium niobate wafer? It's 3 inches in size. I could support a kilojoule pulse going through that thing. And the reason it's no use in the normal quasi-phase matching world, of course, is that the grading K vector is in the plane. So you get no quasi-phase matching if you come in at the surface. But if you could make a set of tilted domains instead of domains that are normal to the surface, then if you come in incident at an appropriate angle, you would refract till you're going parallel to the domains, normal to the domains, and you could have effectively a collinear interaction of the conventional type, but you're accessing it from the surface of the crystal. So it turns out that ferroelectric domains like to follow the ferroelectric axis. So if instead of having the ferroelectric axis vertical, you get a wafer cut at an angle, the domains want to go in that direction. If you apply a big voltage to such a rotated crystal, the first thing that happens is it breaks. There's a large piezoelectric coupling, makes a huge stress, cracks the crystal. If you get smarter and you use a low coercive field crystal like stoichiometric lithium tantalate, you can get a set of domains to go at an angle controlled by a pattern on the top of the wafer. Oops. And this is a phase matching curve versus angle as you come in incident on such a slab. And you can see nicely at Brewster's angle, you get the peak of the second harmonic generation efficiency. So in concept, you can now scale these things to nearly arbitrary powers if you want to do that. There is, again, a bit more material engineering if you really want to make device quality material this way, but the concept, I think, is clear. Okay, let's now talk about, briefly, very briefly, trust me, other patternable media, ones that let us evade these fundamental limits of UV and infrared absorption in the oxides. And rather than go through this list, you can scan it for yourself. There have been quite a few materials people have explored. The two that I want to talk about, oops, I thought I was going to highlight that, but okay. The two I want to talk about are a new ferroelectric that's been quasi-phase matched and is transparent out into the UV. That would be lanthanum borogermanate. The Oxide company has now even a product they'll sell you with this stuff. And the other are these 3.5 and 2.6 semiconductors that give us access to the mid-infrared. So this is a transmission curve of lanthanum borogermanate. And you can see that the fundamental edge is shorter than 200 nanometers, and it has decent transmission to just about 200 nanometers, 210 nanometers, whereas all the other crystals are kicking out somewhere in the vicinity of 350. So you really have access to third and maybe even fourth harmonic of the neodymium YAG laser using this material. And this is a close-up of that absorption edge. This is lithium tantalate. This is LBGO. And this is lithium borate. So you see it's not as good as the best borates, but you do have access to the nice quasi-phase matching technologies if you use this ferroelectric LBGO. So the nonlinear susceptibility is not bad. It's about 0.6 picometers per volt, which isn't bad for a UV material. You can see that they have successfully periodically poled it, and they've even done fan gratings in this stuff. And here you see a third harmonic generation experiment making 355 nanometer radiation using this material. So if you're thinking ultraviolet quasi-phase matching, you should contact the Oxide company. I think I put a link up there. I believe they are now selling this as a real product, and they make custom things. So it's no longer out of the question to do UV quasi-phase matched nonlinear optics. Last thing, our zinc blende semiconductors, common materials like gallium arsenide and gallium phosphide are wonderful nonlinear materials. They have huge Chi2s, 4 times larger than lithium niobate, transparent deep into the mid-infrared, huge thermal conductivities, allowing waste heat to come out. They've only got one fundamental problem. They're cubic. Cubic crystals have no birefringence. You can't birefringently phase match them. So if you want to use these materials and take advantage of this lovely mid-infrared transparency that you don't have in lithium niobate, you need to find some way to pattern these materials. And without getting, again, into the details, since I doubt any of you will ever grow these things, it turns out that in order to invert the structure, the alternating layers of gallium and arsenic, if you could flip which layer was arsenic and which one was gallium, it turns out, given the symmetry of that crystal, that's the same as reversing the orientation of the crystal lattice and flipping the Chi2. To do that, in concept, if you could put a double layer of galliums into your crystal, you could make that reversal happen. But thermodynamics doesn't like this, and so you need a trick. It turns out that germanium is a lattice-matched material that is nonpolar, and if you grow a little germanium film on a gallium arsenide substrate, under the right conditions, you can convince a layer of gallium arsenide to grow with that exact rotation by 90 degrees, or that stacking error that you need to make this film the opposite orientation as that film. If you accomplish that difficult thing, then the rest is straightforward. You have this rotated film, you photolithographically pattern back to the original substrate, so you're now exposing these two orientations, and then you do a thick film growth on this structure, and it follows the orientation of this template, and you can make a rotated, not rotated, rotated, not rotated, under control of the lithographic mask that you used to pattern this thing. And in fact, this works. Here you see domain periods of a couple of 100 microns, 80 microns, 20 microns, and these now can be grown through millimeter or millimeter and a half thick films, so it's very much like mid-infrared periodically poled lithium niobate. And a large variety of interesting devices have been built, OPOs that operate from 2 to 11 microns, octave spanning optical parametric generators in the mid-infrared, high quantum efficiency terahertz sources, all sorts of very analogous systems to what worked in the near and mid-infrared have been extended to the mid and far infrared by using this new material. Okay, we don't need to look at these specific examples. We have to look at one. Bob Bayer and Konstantin Vodopianov built a synchronously pumped OPO that produced 2 to 6 micron frequency comb based on the same kind of schemes that they'd used in Piplin OPOs, but here obviously extending to the mid-infrared. And now this kind of technique is moving towards the full 4 to 12 micron spectrum. Okay, so my summary. Sorry, I'm 8 minutes late. I blame the wine, like I said. Okay, so quasi-phase matching is well established as an alternative to birefringent phase matching. It allows you to systematically process one small family of materials instead of looking for dozens of different nonlinear materials for dozens of jobs. Periodically poled lithium niobate was the first widely used quasi-phase matching material. It had qualitatively better properties, large nonlinear coefficients, non-critical phase matching, high single-pass conversions. And now new materials are emerging that allow those same kinds of behaviors to be accessed in other parts of the electromagnetic spectrum, from the UV to the far infrared and even the terahertz regime. We've discussed a bunch of schemes based on aperiodic quasi-phase matching that allow you to put multifunctions on a chip, engineer different spectral or temporal mixing behaviors, and as we discussed today, a bunch of applications beyond simple coherent sources in classical and quantum optical signal processing and continuum generation are starting to appear. Looking to the future, there's certainly room to improve existing quasi-phase matched materials. We'll touch on some of those subjects tomorrow. There are many more of these kind of devices based on the QPM degrees of freedom that have only barely been touched on. And I think the applications in quantum optics and in signal processing offer a lot of interesting opportunities. So thanks for your attention. If you're up at 8 o'clock tomorrow, we can meet again. But that'll be my last talk, I promise. No more talks after tomorrow.